Okay, let's continue our polynomial and then rational functions. Okay, so now let's move on to section 2.2. We talk about polynomial functions and of higher degree. First of all, we'll learn how to use the transformations to sketch the graph of the polynomial function. Secondly, we'll learn how to use the leading coefficient test to determine the end behavior of the graphs of polynomial functions. We'll learn how to find and use the real zeros of polynomial functions, the sketching aids. Lastly, we're going to use the intermediate value theorem to help locate real zeros of polynomial functions. First one is take a look at graph of polynomial functions. And typically, all of the polynomial functions, their graph is continuous, meaning and it's just smooth and a well-rounded graph. Okay, and that indicates on the graph itself there's no break, no hole, and no gaps, as you can see from the graph itself. Now we will look at a smooth curve from left to right. And we call this type of graph continuous graph or continuous curve. Okay. And now if you look at this particular graph right here, this is a piecewise function. And if you look at right here, this is a gap. You can say it's a gap or jump. So we'll say that this is discontinuous graph, discontinuous. So right here, this is at this point right here, graph is discontinuous or not continuous. And you see the difference between continuous curve and a discontinuous curve. And also the second feature about a polynomial function is it has smooth and rounded terms. You see here increasing all the way to the top of the hill and then start to go down. But again, this is rounded terms. Same thing here, decreasing all the way, and then again you move up a little bit. So, but we see a well-rounded terms. Similarly here, smooth, well-rounded terms. Okay, and that's a typical feature of the graph of polynomial functions. And if you look at function f of x equal absolute value of x, okay, the graph we're going to have a sharp corner at the origin, and this is a typical sharp corner. And we call this kind of behavior corner, and this is typical corner. And this is very useful graph when we talk about discontinuity and differentiability in calculus 1. So keep that in mind. So polynomial function cannot have a sharp turn, but this absolute value function have a sharp turn, a sharp corner here. So the graph of polynomial functions degree greater than 2 are much more complicated to analyze compared to the degree of 1, 0, and then 2. Right? Those are the simplest polynomial functions to analyze. But we still have some tools we can utilize to help us analyze the graph of polynomial functions. Besides point plotting, intercepts, we also have symmetry, and we'll utilize all those tools to be able to get a fairly accurate sketches by hand. And now let's look at the simplest graphs of a polynomial functions. It's f of x equal x to the nth power. So n here is integer, and we can classify into two cases. N is even, and is odd. All the polynomial function with the even power behave very similarly, and all the polynomial function with r power behave very similarly. And let's take a look at some of them. So we know f of x equals x squared. We call this square function. And we see a parabola, and when the power gets bigger, let's say x to the fourth power, as you can see, close to the origin, to the symmetry line, it becomes a wider graph. Okay, so similarly, if you want to sketch x to the 6, it'll become even wider. Okay, so that's how you will see this x to the 6, right? It's even wider graph. Okay, close to the symmetry line, you see a wider graph. Okay, now this is, you say this is equal to x to the 6. Okay, and then all the polynomial function with the r powers start with that y equal to x cubed. Y equal to x to the 5th, very similarly, close to the symmetry point, it becomes wider graph. So if you want to see y to the 7th, see this. Okay, you see a wider graph close to the symmetry point. Okay, something like that. You can label this y equal x to the 7th. And that gives you some idea, what how this r powers behaves, or even powers behave. And then, as you can see, another important characteristic is for the other even power, when n is even, the graph of y equal to x to n touches the x-axis at the x-intercept. This is the x-intercept, so it touches on it, but not close it. But when n is odd, so all this graph of y equal to x to the nth power crosses the x-axis with intercept. We're going through that from left to right. Okay. Now, if you want to sketch the following graph, first of all, we have f of x equal negative x to negative x to the 5th power. First of all, you probably want to start with the x to the 3rd power, something like that. X to the 5th will be slightly, wider graph. So you go this. Then once we have that, we apply the refraction about the x-axis. So this part becomes this mirror image right here, and this part becomes this mirror image right here. So we end up with f of x equal negative x to the 5th power by using the parent function together with the refractions, with the transformation here. And h of x equal to x plus 1 to the 4th power. Here come from y to the x to the 4th power. So that, and then you just basically shift it to the left 1 unit to get our graph. We'll start with this. Now shift all these points 1 unit to the left. Okay. Then we get the transformation function h of x equal to currency x plus 1 to the 4th power. Now let's take a look at leading coefficient test. The leading coefficient test is used to determine the end behavior of each polynomial function. So basically we have two major categories of n's. So we have polynomial function in the general form, but we're going to just concentrate on leading term here, an times x to the nth power. So basically you can ignore the rest of the terms, but just focus on the leading term. So for example right here, f of x equals an times x to the nth power. So the leading term determines the behavior of any polynomial functions. So when n is odd, okay, then n is odd, meaning when x approaches negative infinity here, and then here an is greater than 0. For example, you can think of this as, I'll give you a concrete example, f of x equal to 2x cubed, or something like that. And if x approaches negative infinity here, then f of negative infinity, we're going to end up 2 times negative infinity to the third power, and that becomes 2 times negative infinity. Negative infinity to the third power still remain negative infinity, so we end up with negative infinity here. So that's why it's moving downward right here. So it decreases without bound, right? If negative infinity indicates it decreases without boundary. And on the positive side, when x approaches positive infinity, then f of infinity equal to 2 times infinity to the third power. Infinity to the third power remain infinity, positive. So we get infinity here. As you can see on the right end, it's increasing without boundary. So that's why it's decreasing without boundary on the left, increasing without boundary on the right. And second one, still using the leading term. Okay, an times x to n power. So now we can again use the example. Let's say we're looking at when an is less than 0, so we're going to f of x equal to negative 2x cubed. So x is the r power. Now here, when x approaches negative infinity on the left, f of negative infinity equal to negative 2 times negative infinity to the third power. Negative infinity to the third power is negative infinity. 2 negative turn into positive, so we get 2 infinity. 2 times infinity is still infinity. So that's why on the left hand side it's increasing without boundary. Okay. On the right hand side, when x approaches infinity, f of infinity equal to negative 2 times infinity to the third power. Infinity to the third power remain infinity. It's negative 2 times infinity, that is negative infinity. Okay, that's why on the right end, the function decrease without a boundary. Okay, so this is right end behavior for when an is less than 0 and then n is odd. Okay, and here it's same thing. An is greater than 0 and n is odd. Okay, now let's take a look at when the leading power is even. Okay, so similarly, we can come up with and then when an greater than 0, let's say f of x equal to 2x to the 4th power. And first of all, when x approaches negative infinity, then f of negative infinity equal to and plug into the function, so it's 2 times negative infinity to the 4th power. Negative infinity to the 4th will make it positive infinity, so you have 2 times infinity, that's positive infinity. That's why here the graph increases without a boundary. It's going up forever. On the right hand side, when x approaches positive infinity, f of infinity equal to 2 times infinity to the 4th power. Infinity to the 4th power is still infinity. 2 times infinity is infinity. So similarly, this is increasing without a boundary. Okay. All right, and the last one will be when n is even and leading coefficient is negative. So for example, let's say we got f of x equal -2 x to the 4th power. So this is an greater than 0 and is even. In behavior of the polynomial function, then here an is less than 0 and n is even. So similarly, we analyze through two different angles. First one is when x approaches negative infinity, then f of negative infinity equal -2 times negative infinity to the 4th power. Negative infinity to the 4th power is infinity, so -2 times infinity is negative infinity. So it's decreasing without a boundary. And secondly, when x approaches positive infinity, and f of infinity is -2 times infinity to the 4th power. Again, we plug into the function itself to get this. So we have -2 times infinity. It's -2 times infinity is negative infinity. That's why this graph go down forever without a boundary. Just keep moving down on both the left hand and right hand. Okay. And that's how we utilize the leading coefficient test to determine the end behavior for all the polynomial functions. So you apply to all the polynomial functions. Now, again, let's describe the right hand and left hand behavior of graph of each function. Again, we're gonna just take the leading term. That will make it so much easier. And you could just analyze from there. So here, last one is x to the 5th power. The leading term is a dominant term, and it determines the left hand and right hand behavior of each one of them. So now again, just keep this. So we're looking at f of x equal -x cubed. So when x approaches negative infinity, so now let's plug the negative infinity into the function f of negative infinity equal negative infinity to the 3rd power. So negative infinity to the 3rd power gives us negative infinity, and 2 negative turn to positive. That's why you see that left hand increase without a boundary, so it's keep going up. And secondly, when x approaches positive infinity, so f of infinity equal to negative to the infinity to the 3rd power. Infinity to the 3rd power still remain infinity, so we end up with negative infinity. So right here you see that graph decrease without a boundary on the right hand. So left hand, right hand. And this way to analyze this whole thing is pretty effective, and then it's universal. You can apply to any function you like. So now second one, f of x equal x to the 4th. Okay. So step 1, when x approaches negative infinity, keep the leading term, drop the rest of them. So f of negative infinity here should be negative infinity to the 4th power. That will turn into positive. Any negative number to the even power become positive. So that's why on the left hand you see this function increase without boundary. Secondly, on the right hand, when x approaches infinity, this is infinity here, is infinity, another line. And f of infinity equal to infinity to the 4th power, and remain infinity positive. So that's why it move up. Go up without boundary on both ends, right? On both the left hand and right hand. And the third one is leading coefficient is positive and the power is odd. So again, we keep the leading term. And then you just perform the analysis one more time. X approaches -infinity, f -infinity equal to -infinity to the fifth power. Now make it negative. Right? Number to r powers remain negative, -infinity. That's why on the left hand it's decreasing without a boundary. On the right hand, it's left hand, right hand. X approaches infinity. F of infinity equal to infinity to the fifth. That gives us positive infinity. On the right hand, it's increasing without a boundary. Yeah. Okay, so that's how we analyze the graph using the leading coefficient test. And also we also not just use the leading coefficient test, we can also use intercepts and the minimum maximum points to analyze the graph better. Now, next thing, let's take a look at real zeros of the polynomial function. Real zero, also called x-intercepts. Okay. So it could be shown that polynomial function of degree n. Following statement are true. First one is function f of x and most have n real zeros. So the power determines number of zeros. Number at most n real zeros. That could be repetitive zero. That could be complex zeros. So all possibilities, the most amount of the zero we have will be n. We'll be matching with the leading power. The graph of function f of x have at most n-1 turning points. And turning points usually is what we call relative minimum, relative maximum, for example. Something like this, right? So this is a turning point, another turning point, so 3 turning points. Each one of these turning points either a relative minimum or relative maximum. Depends on the location. Okay. And find the zero of polynomial function is one of the most important tools, also the problems in algebra. Okay, so real zero polynomial function when f is a polynomial function, a is a real number. Following statements are equivalent. X equal to a is a zero of the function f of x. X equal to a is a solution of polynomial function f of x equal to 0. X minus a is a factor of polynomial function f of x. And a comma 0 is an x-intercept of the graph of f of x. Okay, those four are equivalent statements. And they all mean the same thing, right? We're all talking about real zeros of the polynomial function. Yeah, okay, so now let's look at the example. Let's find all the real zeros for f of x equal to -2x to the fourth plus 2x squared. Then determine the maximum possible number of turning points of the graph of function. So first of all, you write a function, and anytime you want to find a zero, you're just basically setting f of x equals 0 and solve for x. So next step, f of x is 0, which means -2x to the fourth plus 2x squared equal to 0. And let's factor by GCF. It's -2x squared goes in the front. So get x squared minus 1 equal to 0. Okay. Then we factor each one of these. We're going to get 3 zeros. First one, we get a couple repetitive 0x equals 0. And the other one is x squared minus 1 equals 0. Then x equals 0, one of them nail down that. The other one will be x squared equal to 1. So x equal to plus minus radical 1. So x equal plus minus 1. That means we have 3 real zeros. -1, 0, and 1. Okay, and then we have 0 repeats twice, right? Meaning we have a repetitive 0 at x equals 0 twice, because the power to the second here. It should be full 0, but we have a couple repeated zeros. And as you can see, and this is a graph of the function. And okay, so we have 3 turning points here because power to the 4th. So number of turning points, it's power leading power 4 minus 1. Turn out to be 3. So here, this is the first turning point, second turning point, and third turning point. For the first turning point, we call this increasing all the way to the top and decreasing, and this is relative maximum. Second turning point, decreasing all the way to the bottom of the valley, and it start to increase. We call this relative minimum. And the reason why it's called relative because you can just constrain the interval in a very tiny little interval. Then in that interval, this point is what we call minimum, relative minimum. But now on the global case, you know that on the global case, there's no minimum here. Minimum doesn't exist. And this turning point here again is increasing all the way to the top of hill and started going down, so this is relative maximum again. Okay, so that's how we analyze this, and we do confirm that there are 3 turning points for this graph function. And now let's take a look at the repetitive 0. Remember from the previous example, for the f of x equal to -2x to the 4th plus 2x squared. When we factor this, we have -2x squared times x squared minus 1. And we get a couple repeated 0 here. And then the 0 repeats twice here. Okay. So our full factor x minus a to the kth power, k is greater than 1, yields a repeated 0, x equal to a of multiplicity k. Okay. So the power is how many times we have a repeated 0. If k is odd, then the graph crosses the axis at x equal to a. If k is even, then the graph touches the x-axis, but not going through that. Right? Do not cross the x-axis at x equal to a. Okay, that actually matters, and we should also pay attention to this particular phenomenon here from a graphical perspective. Now, to graph polynomial function, use the fact that polynomial function contains signs only at its zeros, right? And also for between 2 consecutive zeros, the polynomials must be entirely positive or entirely negative. So actually, I'm going to show you the test interval really quickly. We can do a quick testing interval to come up with this conclusion here. So I'm going to show you here. Okay, and do a test interval, but a test interval comes from the zeros. So for example 3, we know that we have f of x equal to -2x to the 4th. We did it already earlier. We have 3 zeros, x equal to -1, 0, and 1. Okay, and we know that the domain for this function is all real numbers from -infinity to infinity. Now those 3 numbers will cut the domain into 4 intervals. So this is interval number 1, interval number 2, interval number 3, interval number 4. Okay, so now we're gonna do a quick testing interval here. Start with the test intervals. From -infinity to -1. Second interval is -1 to 0. third interval 0 to 1, and last interval 1 to infinity. It totally depends on the real zeros here. And here, from each interval, we're going to pick test value. For the first one, I pick -2. Second one, I pick -0.5. Third one, I pick 0.5. Last one, I pick 2. And we determine the sign of, let's plug into the f of x. So first one, let's see what is f of -2. So it's going to be -2 times -2 to the 4th power, and adding 2 times -2 to the 2nd power. As you can see, it becomes 2 times 16, -32, adding 4, 8. So the result turned out to be -24. So this negative indicates all the y values in this interval will be negative. So that indicates this part of graph is below the x-axis. Okay, that's a conclusion we'll come up with. Okay. So this is a conclusion. We'll be easily verify this in a second. And let's move on to second interval for f of -0.5. Similarly, we plug into the function, original function, and -2 times 0.5 to the 4th power, and adding 2 times 0.5 to the 2nd power. And let's see what that is. Turned out to be 0.375 positive. Again, that tells us all the y values in that interval is positive. So this one is above x-axis. And move on to third interval, f of 0.5. So we get a -2 times 0.5 to the 4th power, adding 2 times 0.5 to the 2nd power. And so we end up with this, it's negative. Will be 0.375 as well. So that means for this particular interval, all the y value is positive. So it's above x-axis. Okay, and then last interval, let's see, f2, that will turn out to be -2 times 2 to the 4th, adding 2 times 2 to the 2nd, so this is definitely negative, so again it's -24, so negative indicates it's below the x-axis. We can easily verify here. See, already graph it here. This part it's from -infinity to -1. Yeah, it's below x-axis. So this -infinity to -1 is below x-axis. -1 to 0 is above x-axis. 0 to 1 above x-axis, and 1 to infinity is below x-axis. Just like what we analyzed from the table, it matches with the actual graph. So if you sketch the graph in a calculator or any like software, you get the same conclusion. But this method is called what we call a testing interval method. It's very useful. You're gonna use a similar method in calculus as well. And this is, so test interval gives us whether the polynomial function is positive or negative, right? Either above x-axis or below x-axis. And we just demonstrated earlier, right? So get all these real zeros first, and then using those real zeros to separate the interval, and we're testing each interval whether it's below or above x-axis. That's what we call the test interval. And last topic in this section is called intermediate value theorem. And let's take a look at how the theorem forms. Let's say we have a number c, x value c is greater than a, less than b. So this is a given condition, given that this happens. Now typically, and then if this happens, if f of c is greater than, is between f of a and less than f of b, as long as f of c is between f of a and f of b, then we say that this is always true, and then this is what we call intermediate value theorem. Intermediate so if this happens, this bound to happen. So it's like causal relationship. So we will call this intermediate value theorem. And then remember, this f of a not equal to f of b. If they're equal to each other, then there's no point of, so this theorem is invalid. Okay. So to summarize what we have for intermediate value theorem, a and b be real numbers. A is less than b if f of x is polynomial function such that f of a is not equal to f of b. Okay. Then in the interval a comma b, f take on every value between f a and f b. Okay. And let's say c belongs to then f of c is between f of a and f of b. And then intermediate value theorem, actually it's very useful in terms of locating the real zeros of polynomial functions, especially back in the time there's no computer, there's no calculator, there's no software, you know, a couple thousand years ago. And a mathematician used this particular theorem to nail down the example approximate location of real zeros. So, and let's say if you can find a value x equal to a, at which the polynomial function is positive, and x equal to b is negative, then you can conclude that function have at least one real zero between this. Right? And it's negative, positive, zero is between negative and positive. Okay. And we know that there's a zero somewhere between those two x values. So for example, let's say we have a function f of x equal x cubed plus x squared plus 1. And if you calculating of f of negative 2, you'll see that it will be negative 2 to the third power, adding negative 2 to the second power, adding 1. Negative 2 to the third is negative 8, adding 4. Negative 2 to the second is 4, adding 1. That turned out to be negative 3. Yep, negative 3 here. So this is negative. And then if you look at f of negative 1, it's negative 1 to the third power plus negative 1 to the second, adding 1. So this is negative 1 plus 1, adding 1, right? So that is a positive 1. And then we know that in between these two values, there's a 0 here, you see, because 0 is between greater than negative 3, less than 1. That means there existing a 0 in between. So this is f of 0 between those two. So no, f of c is between. So C is between -2 and -1. That means between the x value -2 and -1, that's 0 here. Okay, and the thing is, if you keep narrowing down the interval, you'll be able to find out the approximate location for this. So here you go. As I mentioned earlier, if you look at that, so you list all these values for this function here, and especially for f of -1. See, f of -1 equal to -1 to the third power minus -1 to the second, adding 1. And this is -1 minus 1, adding 1. This turned out to be -1, so that's why the y value is -1. F of 0 should be 0 cubed minus 0 squared, adding 1. So as you can see, 0 is between this. That means there should be a f of c in between -1 and 1. I'll give a 0, so that indicates we have a real 0 in between. Real 0. X belong to -1 to 0. Okay, within that interval, we'll be able to locate. Like if you keep narrowing down that, eventually you can narrow down to -0.8 and -0.7, and we will see that it's getting very close to the actual 0 because the y value is getting very close to 0. So you keep narrowing down, you'll be able to get a fairly accurate approximation of the real 0 there. Okay, so that's what we try to figure out here is using the intermediate value theorem to eventually approximate a real 0 between for a given interval. And you can come up with the interval by just try and error, get those different values, and you get a better idea, and every time move closer and closer where the 0 should be located.